All right, in this lecture we are going to discuss the concept of Lorentz invariance. Now, we have seen in the past lectures on relativity that quantities change from one inertial frame to another. For example, the length, the time, right? There's length contraction, time dilation, velocities added in interesting ways, the frequency changes in the Doppler effect. So you might think that there's nothing that's invariant going from one reference frame to the next. Is there anything that is constant aside from the speed of light, right? The speed of light is the same in all reference frame. But is there any other measure which is invariant? And there are other measures. So let's talk about one of them here. In particular, what I propose in this lecture, or what has been proposed, is to generalize the Cartesian three-dimensional distance to a four-dimensional space-time interval. So let's call up a graph here, and let's talk about how to measure the distance between two events, an event being something that has both a position and a time attached to it. So we're going to just go right into it and put the proposal here for a new definition for length in four-dimensional space-time. We're going to label this as delta s, and we're going to relate it as, in fact, delta s squared. My diagram on the right, we can call delta s that length between the two events. I've labeled them by time 1 for the first point here in the bottom left, and time 2 and the one in the top right. But there's also x1. I show an x-axis here and a t-axis there. But also not shown is y1 and z1 for event 1 and y2 and z2 for event 2. I'm just showing the x and time components. But we have this expression for delta s, the quantity squared, and it's going to be a generalization of the Pythagorean theorem, right? So we're going to call this as c times the time difference, delta t, between those two events, quantity squared, and then we're going to subtract off what had been the Pythagorean distance in Cartesian space. So we have delta x squared plus delta y squared plus delta z squared. That's like the three-dimensional distance between these 2 points, the square of it anyway, but we're going to subtract that from c delta t quantity squared. And that's going to be our metric for measuring distances in space-time. And so what I mean by the deltas, just to be more explicit, delta t is time t2 minus time t1. And delta x is position x2 minus position x1, and so forth for y and z. So the deltas are these differences in position, say, either in x or in time or in y and z, for example. All right. It can be shown, and we will show, that this metric, this definition for something generalizing distance, it's kind of a space-time distance, is invariant under Lorentz transformations, so is the same in all inertial frames. Therefore, for something that is the same in all inertial frames, we're going to refer to that as a Lorentz invariant quantity. Okay? And this is one example of such an invariant quantity in space-time. Now let's go through and just prove to ourselves that indeed this must be the case. All right. So let's consider two events that happen in a rest frame S prime. For example, a particle is created and then it decays. And we'll put that particle creation and decay at the origin. So if we put it at the origin, then x1 prime, y1 prime, and z1 prime are all 0. And let's say it was created at time t1 prime of 0. Everything's 0 for all the 4 coordinates. Event 2 is when the particle decays. So when it decays, if we're in the rest frame of the particle, then it has to stay at the origin. So x2 prime, y2 prime, and z2 prime are all 0. But the particle may have lived for a time t naught in its rest frame. So time t2 prime is t naught. And now let's plug in to that formula I just gave you on the previous slide. That delta s prime squared is c delta t prime squared minus, remember, the sum of the squares of the spatial deltas. So it's minus delta x prime squared, minus delta y prime squared, and minus delta z prime squared. But this is rather simple to compute, right? Delta t prime is just t2 prime minus t1 prime, so t naught minus 0, so that's just t naught, multiplied by c, so it's c t naught quantity squared. So I get c squared t naught squared. But as the particle remained at the origin from its creation and its decay, those deltas are 0, and so I get that it's just c squared t naught squared for delta s prime squared. Or in other words, taking the square root, that space-time interval is c t naught. So that's in one frame. Now let's make a Lorentz transformation to another frame S that is moving at a velocity v with respect to the rest frame. All right, well, if we do a Lorentz transformation, we got to pull up those equations. So we got to go back and look at what we got out of those lectures. And we see if we boost along the x-axis, that to go from the prime coordinates to the unprimed, let's say from x prime to x is gamma, remember that's the shorthand, 1 over square root 1 minus v squared over c squared, times the quantity x prime plus vt prime. Transverse directions are not affected by the Lorentz boost. So if we're going to boost along the x-axis, y prime and y are the same, and z prime are the same, and they're going to remain at 0. Time changes though, right? There's time dilation, and in more general, in the Lorentz transformation, time and spatial dimensions get mixed up. So to get to the time in frame S, I have the t prime time in frame S prime, and then there's a v, the velocity of the initial frame with respect to the other, times x prime over c squared, and then all that times gamma. Right? So now we've got to try to compute our expression for that space-time interval delta S in this frame S's, the frame S inertial frame. Okay, so we got to work out some deltas here. We know that in the primed frame, all the coordinates were 0. And so for the initial production of the particle, even t prime was 0. So if I'm trying to compute x, if x prime and t prime are 0, then x itself will be 0. So x1 is 0. What about x2? Well, x2 depends on x prime and then t prime. X prime stays 0, but t prime has become t naught. And so in this formula here, I'm going to get a gamma, a v, and a t naught. So x2 is gamma v t naught. That means the difference in those quantities is 1 minus the other. It's gamma v t naught as well for delta x. Now delta y and delta z, since those coordinates are unaffected, those deltas remain to be 0. What about time? All right, we have this expression here. So we can work out time at the first event and time at t2, the second event. So t prime at the first event is 0, x prime was 0, so t1 is going to be 0. What about t2? Well, t2, in the prime frame, t2 prime was t naught, but x prime was still 0. So this is 0, but I have t naught here, and so I'm going to get gamma t naught. So delta t is gamma t naught. So I have delta t, I have delta x, and I also have delta y and delta z, which were both 0. So great, I can compute this interval that I proposed on the previous slide. Delta s squared is c delta t squared, and then minus delta x squared, minus delta y squared, minus delta z squared. Well, c delta t squared is going to be c times gamma t naught for delta t, quantity squared. So I get a c squared, gamma squared, t naught squared. What was delta x? Delta x is gamma v t naught. I'm squaring it, so I'm going to get a gamma squared, a v squared, and a t naught squared. The delta y's and delta z's were 0, so they don't add anything or subtract anything, as the case may be. All right, so let's try to simplify things a little bit. Right, I can see that I can pull out, for example, a c gamma t naught in the equation above. And if I pull that out, I'm going to have a well, I should say the square of that I'm going to pull out. If I pull that out, I have c squared gamma squared t naught squared. That's this first term, so I'm going to multiply that by 1. The second term has almost the same factors, but it has a v squared instead of c squared, so I better divide by c squared and multiply by v squared. So it's going to be 1 minus v squared over c squared times c squared gamma squared t naught squared. Okay, so I've done that. Now what I can do is expand out the gamma squared here. Gamma squared is 1 over 1 minus v squared over c squared. So that is going to go here, 1 over 1 minus v squared over c squared. But I had a 1 minus v squared over c squared in the numerator. So what's going to happen is that 1 in the numerator is going to cancel with the 1 in the denominator. And what I'm going to be left with is just c squared t naught squared. Or put another way around, delta s, when I take the square root, is just c t naught, but c t naught is indeed what we found up above in frame s prime as well. So the interval is indeed invariant. Okay, so we've shown that, in fact, taking this Lorentz transformation from one frame to another, we can show that this space-time interval that we've defined, which one way to define it is just looking at this expression earlier in the page, delta s squared is c delta t quantity squared, then minus delta x quantity squared, minus delta y quantity squared, and minus delta z quantity squared. All right, so we've just learned our first Lorentz invariant quantity.